Hello, hope you guys can hear me. Let me just change a few things. Okay, let me change to full screen. Okay, so I think in my last derivative stream, I did related rates. This one I will do linear approximation and maybe maxima and minima too. Let's see. It will take forever to load. And the answer key, chapter 4. Okay, so linear approximation of a function at a point. Consider a function f that is differentiable at point A. Recall that a tangent line to the graph of f at A is given by the equation y is equal to f of A plus the derivative at A times x minus A. Okay, so let me write it down. Y f of A plus here's here's f of A, and then here is a tangent at this point A, then f A, and then the tangent, and then this is equal to I think this is the y-intercept for this line. So this is C. This is approximately. So this gradient is about the same as if I take a very close y point and x point. So no, y point and f, like this, some x y point, oops, that's very close, and then divided by x minus a. I think it would be easier if I write t of a. So tangent at a. Find the linear approximation of this. So let's say f of x is equal to root x at 9.1. It's about the same as whoops, wait. So this is 3. The derivative is like that, I think. Then this would be 3. Then 0.1. Let me use a calculator. Uh, 0.23, 3.2666. Now, why did I get this wrong? Yeah, I wrote it in my calculator wrong. Find the linear approximation of f of x at sine x. Okay. So at pi over 3. So what we are finding, wait, hold on. This is in degrees and this is in radians. Or it hold on. 180 degrees is pi radians. So 60 degrees is pi over 3 radians. Sixty, 60, 60. Sine of 60 is root 3, and then the derivative is cos, which is half. And then 62 minus 60. So then this is equal to 1.866. Hold on, where did I get wrong? I don't understand where I got wrong. Sine of 60. So 0.866. Okay, let's try it another way. D of x is approximately f of pi over 3. Let's just do it, pi over 3, then x minus pi over 3. D of 62. What is 62? So wait, 60 degrees is pi over 3 radians, and then 60 times it by this is equal to pi over 3 times it by this. Sine pi over 3 would be the same, just making sure, plus it with cos. That's what we have. And then x is 62 pi or 180 minus pi over 3. So there, I multiply this by 60, then I get 2 pi over 180, and then pi over 180. I guess it's this, plus pi and this gives me a better answer. Oh, why didn't this work? I'll have to ask Reddit. Find the linear approximation of this. at x is equal to 0. So then x minus 0 is just x. Well, what's n? F of 0 is 1 to the power of n, which is just 1. The derivative is n times wait. Hmm. Since this is 3, since n is equal to 3, I think it's 4.03. Why is it? Oh, I see. That's why. We have seen that linear approximations can be used to estimate function values. They can also be used to estimate the amount of function changes as a result of small change in the input. We define a related concept, differential. Okay. Find dy and evaluate when x is equal to 3 and dx is equal to 0.1. Let's try this. Let's try the first one. What is it? 4.8a. So I just have to substitute. What is it? 3 plus 1 4. 4 times 2 is 8. Then it's 0.8, right? So the change in y is 0.8. Okay. Differentials can be used to estimate the change in the value of a function resulting from a small change in input values. Instead of calculating the exact change in y, however, it is often easier to approximate the change in y by using a linear approximation. Consider a function f with an input that is a measured quantity. Suppose the exact value of the measured quantity is a, but the measured value is a plus t of x. We say the measurement error is t of x or delta x. As a result, an error occurs in the calculated quantity f of x. This type of error is known as a propagated error and is given by this. Since all measurements are prone to some degree of error, we do not know the exact value of a measured quantity, so we cannot calculate the propagated error exactly. However, given an estimate of the accuracy of a measurement, we can use differentials to approximate the propagated error, delta y. Isn't delta y and dy the same thing? So wait. So dy f of x times dx. So dx takes the difference. No. Yeah, it takes the delta x then times it by the gradient. Okay, I understood this. Change in y. F of a plus dx minus f of a. Here's a. F of a plus dx. So let's say, let's take a very large dx, just for the sake of example. So this is f of a plus dx. Minus it with f of a. And then this over here, dx times it by k. I think I understand. Shouldn't this be? Never mind. So delta y would be the actual value, right? Instead of calculating the exact change in y, however, it is often easier to approximate the change in y using a linear approximation. So linear approximation is the same thing basically. Plus what's the difference between this and this? Because delta x is over here, basically the difference, and then we are calculating the gradient. This is the bias basically. It's f of a, no, f of a plus it with the change. So we are calculating this. Then this is approximately equal to this. Should I do a maximum and minimum as well? Okay, maximum and minima. Absolute extrema. Consider the function x squared plus 1 over the interval minus infinity to infinity. As x approaches either infinity, f of x approaches infinity. Therefore, the function does not have a largest value. However, since x squared plus 1 is greater than or equal to 1 for all real numbers x, and x squared plus 1 is equal to 1 when x is 0, the function has its smallest value 1. we say 1 is the absolute minimum and it does not have an absolute maximum. We say f has an absolute maximum on I at c if f of c is greater than or equal to f of x for all x in that interval. We say f has an absolute minimum on I at c if f of x is lower than or equal to f of x for all x within that interval. An absolute minimum or a maximum is an absolute extremum. Extreme value theorem. If f is a continuous function over a closed bound interval a and b, then there is a point a and b at which f has an absolute maximum over a and b, and there's a point at which f has an absolute minimum over a and b. Okay. So this is basically that absolute maximum and minimum exist. Local extrema and critical point. If a function f has a local maximum at c, if there exists an open interval I containing c, such that I is contained in the domain of f and f of c is greater than or equal to f of x for all x within that interval. Wait, I don't understand this definition. This is a local maxima, this is a local maxima, this is a local minimum. Okay, I got it. That means we can draw an interval around it such that f of c would be the maximum or minimum. Let's see, be an interior point. We say that c is a critical number of f if the derivative is not 0 or the derivative is undefined. If it's 0 or undefined. Okay, yeah. For a local maxima to exist, the derivative has to be 0 or undefined. Fermat's theorem, if f has a local extremum at c and f is differentiable at c, then the derivative at c is 0. Okay. So all absolute extrema are local extrema, right? Find the absolute maximum and absolute minimum over the specified interval. State where those values occur. Wait, hold on, sorry. Um, okay. Uh, so derivative. Uh, okay, and when it's 0, sorry, yeah, when it's 0, x is 2 over 3. And for b, wait, hold on. 2 over 3 is 0.6666. Wait, hold on. Whoops. I made a mistake here. It's 3 over 2, not 2 over 3. Then f of 3 over 2 is 1 over 4. This I don't understand. This is 2x if I derivate it. And then, sorry. Minus 2 over 3. and if this is 0, yeah, if this is 0, so is it like this? This is maybe. Yeah, I think something is coming up. I will have to end the stream. Sorry, sort of an emergency. Sorry, I was not able to focus. I think tonight or maybe tomorrow I will continue this.